In this fourth and last part of the tutorial, we will generate PowerFlow results using GridCall. As we have seen previously, GridCall is a tool, a Python package for static power system computation such as PowerFlows. Our main idea is to generate records using PowerFlow results from GridCall to populate our models in such a way that if we compute different PowerFlow conditions for a given system, by changing the PowerFlow property of this record, we will be automatically updating the different PowerFlow variables in the grid, such as generators P and V, loads P and Q, and buses B and delta. So the input to GridCall will be a PSSE raw file containing the information of the static network that we will be using for a PowerFlow computation. But it is possible to create your own GridCall model in case you don't have a PSSE file available. Our main reason to use raw files is that they are largely available on the network for several standard test case systems, but also because we wanted to compare the performance of GridCall and PSSE. We found out that we are able to get the same solution, practically the same solution, up to solver tolerance for PowerFlow computations with both GridCall and PSSE. Finally, once we generate the PowerFlow using GridCall, we would like to we'll export it into a format readable by Modelica using a function called GridCall2rect that is included into the pf2rect folder accompanying this tutorial. Finally, if you generate several PowerFlow results, you will see that it is pretty straightforward to change the PowerFlow condition on your model in the model. To conclude, we would like to encourage you to develop your own models. We have a database of application examples within OpenIPSL. But if you have a model that you think it would be a good addition to our library, we encourage you to do a pull request at our GitHub. So let's get our hands dirty and generate PowerFlow results for our Modelica OpenIPSL models. So we are back into the SMIB folder with our Jupyter Lab and Windows Explorer here. And the main difference here is that I have copied and pasted the PSSE files folder that contains the PSSE information of the SMIB system, and we will use the raw file as an input to GridCall, so that we will parse this raw file into a GridCall object, and we will start working from then onwards. Another different thing was that I copied and pasted into our main directory this zip file that is called 032320 hourly basis, and that's the information that we will use for the time series PowerFlow computation at the end of this video. So let me extract this, and let's extract it. And it created this folder, so let's just work with this hourly basis directory. So that zip file and this PSSE files, you find both folders in the GitHub repo accompanying this tutorial. So now let's create a single PowerFlow result with GridCall, and to do it, let's launch a new Jupyter Lab. Let's call it generate PF base case, and the first thing that we will do is import the different dependencies that we require. So we need to import everything within pf2rect. So let's change first. Oh no, we're fine. Let's import everything from pf2rect. Also, let's import OS, and the new thing that we have to do is to import GridCall. So the way to do it is, there are several ways to do it, but I like this one. So from gridcall.engine we will import everything. And finally, in this preliminary section, since we are working with version 2.0 of OpenIPSL, I would like to define a variable on top for it. So this would take some time to load because GridCall is a huge package, but with the latest version of Gridcal, they have improved a lot the efficiency of the library. So as you may have noticed, it didn't take more than a few seconds to import all the packages. Now what we are going to do is so let's here in the preliminary, well, let's not reload the packages, but this should have been included in the preliminaries, and it's that we need the path, we need the absolute path to the folder containing the model information, and we will call this variable data path. So that's the same as we did in the previous video, is just the absolute path to this SMIB directory. So actually, let me just, for simplicity, let me just copy and paste it from the previous notebook. And that's it. That's everything we need regarding some preliminaries. Now we will create a Gridcal model using the PSSC raw file that we find here under PSSC files in the SMIB folder. So to do it, first we will create an object called grid that for the time being is none, and then we will instantiate a parser object in Gridcal. So that parser object belongs to the file open class, and what we need to pass inside the file open class is the path to the raw file. But the raw file is inside the SMIB subfolder. So we can do data path. We will join it with PSSC files, and PSSC files we will join it with SMIB base case.raw. So we would like to join all of these paths, right, as we did previously, and just to make sure that nothing is working as it shouldn't, let's encapsulate all of these path calls within an OS path apps path. So this will create an instance of file open, the file open class that is the Gridcal parser that we will store inside file handler. And then, so basically, this is the instantiation of the Gridcal parser, and now we will create a Gridcal grid object from the parser. So here in grid we would like to file handler that open. So we will open this raw file and we will save it as a Gridcal model. So once we are here, for example, we can get access into the grid class. So we can, if we would like to do modified version of the SMIB model, we can use some of these other methods. Or if we want to have a look, for example, into the names of the buses, then I forgot if this is a function or this is an attribute, but it's not complaining. So, well, this field is empty, and of course, it's Murphy's law. So I picked something that was empty. But for here, in get buses, we will get an array of the different Gridcal objects that are used for storing the buses. Great. That's for the grid. So now we have a grid model and we would like to do a power flow computation, but first we need to set some power flow options, and the options are pretty straightforward here. So basically the options are also an object in Gridcal of type power flow options. The first one that we need to pass is the solver type, that in our case we have said previously that we will use Newton-Raphson. Then we would like some verbosity, just to make sure everything is working fine. And let me show what other flags could you add here. So for example, there is a flag for initialize the power flow with an existing solution, that in this case we will set to false. There is another one for allowing multi-core computations, but since this system is small, we can just set it to false. Then finally, some more common options of the power flow computation, such as the solver tolerance, that we will set to 1 to the minus 6, 10 to the minus 6, sorry, and the maximum, so let's go back here, the maximum number of iterations, let's set it to 99. And finally, an important flag for any power flow computation, that is the control Q option. So GridCall has several, you can go and check for them in the documentation, but the one that we will be using is reactive power control mode .direct. So that would be it concerning the power flow options. And these options are passed to another object that belongs to the power flow driver class. So we need to pass the options, but also the grid model, since this power flow driver will be constrained to the grid topology that we have. So let's run this cell again to have the options and the driver available. And now let's run a power flow computation. So we just invoke the run function of the power flow driver object, and then internally it's taken care of computing the power flow solution for us. So now the power flow solution is complete, and the results are stored in the field PF results. So if we would like, for example, to get information about whether the power flow has converged or not, so there is a flag that is telling us that for this case the power flow solution converged. We can check limits. So let's see what this function does. Well, we need to pass some arguments, but I don't want to spend a lot of time here. Let's check, for example, the complex power at each of the buses. So this is what it found, and we can play with this, but I would like to skip it and jump directly into the record generation using this power flow result. So now what we are going to do is to invoke the GridCall to rec function. So here we first need to pass the grid object that we created in GridCall. Then we pass the power flow driver, where the power flow result is stored. The next argument is the model name. So here is basically the name of the package where our model is contained, that in our case is SMIB. Then we need to pass the path of the folder where the SMIB is stored, that in our case is data path. And after this, we have some additional flags to basically, for example, pfnum will label the different power flow results according to this number. So this is more or less as an identifier for the different results, and this would help us automate power flow computation, as we will see later, for the time series power flow. Likewise, we can, if we want to see the power flow results in CSV form, we can change this export PF functions flag to true. And finally, let's specify that we are working with OpenIPSL version 2. So here we're making use of the flag that we defined above. So before executing this cell, I would like to go back here and go inside the PF data folder. So we have, for the time being, we only have the different the record template that we created in the previous step. So let's now run GridCall to rec, and you might see here that GridCall to rec created a power flow record file called pf_50.mo, and he also created a directory called pf resort csv that is basically here because we enabled the export pf results flag. So if we navigate to the bus data subdirectory, we know that we can notice that there is a new pf bus Modelica file here, the same for loads, the same for machines, and the same in the case of transformers. So that is what GridCall to rec does, and that's the way in which we can generate a simple power flow result using GridCal. So now in part B of this fourth part of the tutorial, we will generate a time series power flow result using real data.